Scientists analyzed climate records from 66 million years ago and found that these natural phenomena caused significant environmental alterations prior to the meteorite impact. How they realized. Throughout the history of the Earth, different natural processes have generated changes in the climate. A group of scientists analyzed ancient climate records and detected that, in the past, these variations were influenced by phenomena such as volcanic eruptions and changes in solar radiation. These events altered the atmosphere, modified the composition of the oceans, and caused transformations in ecosystems, even before the impact of the Chicxulub meteorite, which marked the mass extinction of the dinosaurs at the end of the Cretaceous. The study, conducted by a team at the University of Bremen and published in Science Advances, synchronized climate records from the Atlantic and Pacific Oceans to examine events that occurred 66 million years ago, before the disappearance of the dinosaurs. The analysis revealed that massive volcanic eruptions from the Deccan Traps in India altered the atmosphere and ecosystems, showing how geological events can impact global climate. The eruptions, which covered wide regions with basaltic rock up to 2 kilometers thick, released large volumes of CO2 and sulfur dioxide, SO2, gases that modified the chemical composition of the oceans and altered global weather patterns. The formation of these basaltic rocks and their subsequent weathering left a geochemical imprint on the oceans, explained Junichiro Kuroda, a scientist at the University of Tokyo. Analysis of high-resolution geochemical records identified variations in osmium isotope composition in the Atlantic and Pacific Oceans, which coincide with the most intense phases of volcanic activity in the Deccan Traps. A prehistoric climate change. According to experts, the Deccan Traps were linked to mass extinction events in Earth's history. These eruptions released large amounts of volcanic gases, altering the global climate balance. According to the study, the first eruptive phase, which occurred approximately 66.49 million years ago, was marked by sulfur-rich emissions, which likely generated temporary global cooling and significant stress on local and global ecosystems. The second phase, dated to 66.28 million years ago, was characterized by more carbon-rich emissions, which contributed to significant global warming. This abrupt climate change, according to the researchers, may have exacerbated environmental conditions before the meteorite impact in Chicxulub, Mexico, which marked the end of the Cretaceous period. The volume of basalt erupted during this initial phase was much larger than previously thought, and the associated emissions of carbon dioxide and sulfur dioxide had varying effects on the global climate system. The results also suggest that sulfur emissions during the first phase may have reduced global temperature by reflecting solar radiation, while carbon emissions from the second phase contributed to global warming by intensifying the greenhouse effect. To achieve this level of detail, the researchers synchronized climate records from the Atlantic and Pacific Oceans using rhythmic changes in solar insolation, a method described as a metronome by Westerhold. This approach allowed the team to align the geological records with an accuracy of up to 5,000 years, an extremely short interval in geological terms. Having the geological records perfectly aligned in time allowed us to observe that two large changes in climate and biota occurred simultaneously in both oceans. The synchronization of these records was made possible by the analysis of isotopes of osmium, a chemical element that acts as a geochemical marker in marine sediments. According to Kuroda, these changes reflect the weathering of the basaltic rocks of the Deccan Traps, which allowed the eruptive phases to be identified accurately. This approach also revealed that volcanic emissions had differentiated impacts on marine ecosystems, as evidenced by changes in the fossils of benthic foraminifera, single-celled organisms that inhabit the seafloor. In addition, the researchers combined this data with astronomical models to develop a detailed chronology of climate and volcanic events, allowing them to identify correlations between volcanic eruptions and changes in the carbon and oxygen cycles in the oceans. In doing so, they were able to get a clearer view of how Earth's internal and external forces interact to shape the climate. According to the scientists, alterations in foraminifera and other marine life suggest that volcanic emissions threw local ecosystems out of balance before the asteroid collision, which marked the mass extinction at the end of the Cretaceous.